So in the previous modules, we've talked about entropy and configurational entropy. Now I want to look at thermal entropy. So this is going to be related to the vibration of atoms. And it could also be ions, if we're talking about our ceramics, in a solid. And therefore, we're talking about the uncertainty of the value of its energy. So we're talking about the vibration, and that, of course, goes to thermal, because the higher the temperature, the more vibration a given atom or ion in a solid will do. So we've already talked about how we can define entropy in terms of heat, and so that's the equation we're going to use here. So if we're looking at constant pressure, and a lot of processes that we look at are at constant pressure, because if they're done at just basic atmospheric conditions, right, the pressure isn't changing. So we can calculate that for thermal entropy. So we're also going to, and the reason we want to do this is because that allows us to also look at heat capacity, right? We used heat capacity data when we talked about enthalpy to calculate enthalpy content. And so here the way we define entropy also allows us to use that same data. So let's kind of just show that. So here again, we're using the D for the differential value, so a small increment of entropy change. In this case, this subscript T for thermal. And we define this, so equal sign plus an extra one, as that quantity of heat, so small delta Q, and then it's reversible energy, reversible heat, and then that's divided by T, right? So this was our definition that we talked about in the previous module, but we know that this reversible heat is also equivalent to heat capacity, and so we can also define entropy as heat capacity over temperature, and then multiplied by the differential temperature. So again, if we want to look at the overall change of entropy between two states, we're going to take the integral, and in this case, we're going to use a reference point of 0K up to whatever temperature we're after. And so that's going to be heat capacity, constant pressure heat capacity, divided by temperature times dT. Right? So this is what we can use to calculate the entropy content, the thermal entropy content, as well as the differential, by looking at heat capacity, because again, this is values that are typically tabulated, and we can find those and then apply this integral.